everyone. Today we are going to begin our next chapter, Chapter 7, Volcanoes and Other Igneous Activity. Like before, I will post links for all the YouTube videos on the Blackboard site. Additionally, I am going to post a link to another video that is completely optional to watch. It's kind of geared towards a younger audience, but it does a pretty good job of giving a generalized overview of volcanoes and volcanic activity. And it might be kind of cool to see what kind of concepts from this chapter you can pick out in that video. So, to start out, one of the most famous eruptions, especially kind of in our lifetime, is the eruption of Mount St. Helens in Washington on May 18th, 1980. Most people tend to think that all the mountains out west are part of the Rocky Mountains. This is not true. Mount St. Helens is actually part of a chain of volcanoes called the Cascade Mountain Range, and this is in the northwestern U.S. and the western Canadian region. So they move through Washington, Oregon, Northern California, and I'll be honest, my knowledge of Canadian territories is not great, so I'm not actually sure which region that is. So the Cascade Mountain Range is caused by the subduction of the Juan de Fuca plate, and as it subducts, it causes the Cascadia Trench out at sea, and at some point during its subduction process, the gases become volatilized, and this is where you get this mountain range forming. So this mountain range is actually caused from the subducting oceanic crust under the continental crust. So, just some facts about Mount St. Helens. It was the largest eruption in North America in historic time. It was a 24 megaton blast, which is approximately equal to the explosive force of the bomb dropped on Hiroshima. This blast actually lowered the elevation of the peak of Mount St. Helens by over 1,300 feet. It discharged 540 million tons of ash, and it covered over 22,000 miles to the east and southeast of the mountain. 59,000 people died, many of whom are actually still missing. There are bodies that were buried under the debris slides that have never been found. There were glaciers on Mount St. Helens at the time. Those glaciers were vaporized, and the steam mixed with the ash to actually create extremely hot, almost boiling mud flows, which moved downhill at speeds of higher than 90 miles per hour, destroying everything it encountered. River valleys around Mount St. Helens were actually buried with up to 150 feet of debris. So you can see I'm not sure if this is lake or river, the body of water here, and afterwards it is just completely covered in ash and debris and rock from the eruption. I was going to try and play this video for you, but I don't think it's going to work within this. Please watch this video. It is a series of photographs that were taken right at the time of the eruption. It gives a really good sequence showing how the side of the mountain actually bulges up with all the pressure and energy from the magma before actually exploding upward and then collapsing down into the chamber it basically created and sliding down slope. So it shows this really big expansion and just sliding downhill in the massive landslide that's created. In contrast to the large single explosive action of Mount St. Helens, Mount Kilauea in Hawaii, please, if I'm wrong, someone correct me. This volcano has actually been undergoing constant eruption since 1983. This is one of the largest active volcanoes in the world and is one of 5 major volcanoes on the island of Hawaii. This volcano initially formed 300 to 600,000 years ago, but over 90% of its surface is covered by lava that is less than 1,000 years old. This is primarily because this continual eruption since 1983 is constantly creating new lava that covers the surface, and preceding events would have done the same thing. So even though it is over 500,000 years old, the exposed lava is much younger, or the exposed rock material from the lava. I'm sorry. In 1790, an eruption killed several hundred people, but several people have died in the latest eruptions. The crater for this volcano has a circumference of 8 miles and is surrounded by a wall of volcanic rock of up to 500 feet tall. The actual crater is calculated to be about 3,600 feet deep. And here's a video of an eruption there. Please watch this video also just to get a feel for the difference between the very massive instantaneous explosive event of Mount St. Helen and the slightly tamer eruptions on the island of Hawaii. So why do these two volcanoes behave differently? And again, watching those videos is going to be really key to understanding this. So let's start with Mount St. Helen on the right side. Mount St. Helen is what is called a composite or a stratovolcano, and we'll get into that term in a bit. Composite and stratovolcanoes have short, violent eruptions following extremely long periods of calm or dormancy. The magma is very viscous or thick, which does not allow gases to easily escape, so internal pressure builds up. So when we talk about viscosity, water has very low viscosity, so it flows very easily, whereas like corn syrup or molasses has a very high viscosity, so it moves very, very slowly. The crystallized lava associated with composite stratovolcanoes is andesitic in composition. So this is continental crust material. So remember we talked about basaltic versus andesitic. So andesitic is one of those lighter colored minerals, your feldspars, your quartz. Basaltic would be more of your hornblende, amphibole, olivine. So composite stratovolcanoes, specifically Mount St. Helens, this one originates from subduction and remelting of tectonic plates. And it is shaped like a cone as lava and ash are deposited close to the crater and build up high angle slopes. That's what gives it its really structured mountain shape. Whereas in Hawaii, this is what is called a shield volcano. These are relatively peaceful and long-term eruptions during active periods. The magma is very non-viscous, so very fluid, so it acts more similarly to kind of like a water flow. This allows gases to easily escape. The internal pressure doesn't build up there. The crystallized lava is basaltic in composition. This is oceanic crust, and originates over a mantle hotspot. So we talked about the plate tectonics. It's not associated with actual plate subduction, but there is believed to be a magma plume under the crust that is extremely hot, creating the Hawaiian island chain. And it is shaped like a slightly raised shield as lava spreads out far to build up low angle slopes. Because the lava is so viscous, it flows a lot faster, it flows a lot further. So instead of just erupting and then holding in place, it erupts and spreads out, giving it that much lower angle. So the nature of these eruptions. The characteristic of a magma is what determines the violence or explosiveness of an eruption. So like we talked about the viscosity or resistance to flow, and this is based off of composition, so the silica content, higher silica content, plagioclase, quartz, those tend to be more viscous. Temperature can impact viscosity and the amount of dissolved gases. So this table is in your book, but it just briefly looks at the composition. So if you have a basalt or a mafic composition, so less silica content, you have lower gas content. The eruptive temperatures are usually about 1,000 to 1,200 degrees, so the higher the eruptive temperature, the more viscous it is. Like if you heat up syrup or if you heat up molasses, it flows a lot easier because of the activity and energy of the molecules. And then its tendency to form pyroclastics. It does not form pyroclastics, which we will discuss in a minute. And tend to create shield volcanoes, basalt plateaus, and cinder cones. Okay, and this is actually incorrect. So the viscosity, basaltic would have the highest viscosity. It flows the easiest. The rhyolitic would flow the least. So andesitic is an intermediate. So you see middle ranges, a composite cone. Rhyolitic or felsic, which has the most silica content, lower temperatures, and has the greatest tendency to form pyroclastics, and you get pyroclastic flows or lava domes. So how do you decrease magma viscosity? You can increase its temperature, you can decrease its silica content, So the rhyolitic and acidic magmas are greater than 70% silica, which form very short flows, but the basaltic are more fluid. You can add water. If you add water, you're changing the composition of that flow. So we get different extrusive igneous materials from volcanic activity. The first are our lava flows. You can get pohoihoi on the left, which are ropey texture. These are typically from hotter, more fluid basaltic lava. And then on the right, you can actually get what are called a'a. These are both Hawaiian terms. A'a are jagged textures. This is from cooler, less fluid basaltic lava. And the joke is that it was named that because it is very jagged and sharp and is painful to walk on. Lava tubes are a geologic formation that actually develop in pohoihoi lava, and they serve to insulate lava and allow it to travel for many miles. So what happens is you've got the pohoihoi, and you see how up here it is cool, but in the interior you've still got that very hot red lava. So what happens is the exterior cools, but that interior is still hot enough to keep flowing. So it flows and it's cooling and it's creating this tunnel to kind of insulate the temperature, keeping the core of the inside warm, allowing it to travel a further distance until finally when the system exhausts itself, there is no lava left in the very beginning stages of that pohoihoi. And so all you're left with is this hollow tunnel. So here's just some examples of lava tubes. This is actually a graphical representation of the lava that would be in here. And here's what a lava tube would look like decades after an actual event, when you're able to walk through it. So which sample of rock here is a'a and which is a sample of pohoihoi? When we talk about lava, we typically think about the pictures we just saw, because 90% of lava is basaltic. It flows in thin, broad sheets or ribbons, and can flow from anywhere from 10 to 300 miles an hour, and can even flow up to 30 kilometers an hour going downhill. Only about 9% is andesitic or intermediate, and less than 1% is rhyolitic. Rhyolitic has very thick flows that are imperceptibly slow and don't flow beyond a few kilometers from vents. So in addition to lava, we get a few other extrusive igneous materials. We get gases, which can be 1 to 6% by weight of the total magma. These actually cause atmospheric reactions, and the atmospheric reactions can have as significant an impact as the actual lava. So we have water vapor that's trapped in there and is the most abundant gas in the volcanoes. We have carbon dioxide, which is the second most abundant volcanic gas, and then we have sulfur dioxide. This contributes to the pollution when combined with the water vapor in the air to create sulfuric acid. This is how we get acid rain. Okay. The sulfur dioxide released into the atmosphere can actually cause slight short-lived cooling of the atmosphere as they form sulfate particles in the air, which tend to reflect sunlight back to space. Okay, so it creates this additional layer within the atmosphere that doesn't allow the solar radiation through that typically heats the Earth's surface and can cause short-term cooling periods that have actually been traced through history. Next are pyroclastic materials, known as tephra. This is the ash or hot fragments of rock and glass that are ejected during a volcanic eruption. These fragments range in size from less than 2 millimeters to many feet across. So the types are the ash or dust. These can be fine glassy fragments. You get cinders, which tend to be about pea-sized material. Lapilli, which are tiny walnut-sized stones. And then particles such as blocks, which are actually hardened lava. Or bombs. Bombs are actually ejected as hot lava and then cool in the air. The exterior cools, the interior is still very hot, and when they hit the ground, that impact can also create kind of an expansion of that interior hot lava. Additionally, you can get scoria and pumice. Remember we talked about these when we were talking about rocks. So these are vesicular rocks that are ejected from magma. The scoria are basaltic composition. Those are those red or black. And the pumice are the ones from andesitic or rhyolitic. Those are the pink or kind of gray shades. So here's just the picture from your textbook explaining the classifications. So volcanic ash is classified as under 2 millimeters. Lapilli are between 2 and 64. And then you have volcanic bombs and blocks. So let's talk about the actual form of a volcano. So volcanic landforms are the results of many generations of volcanic activity. They're very rarely caused by a single volcanic event. So an eruption starts at a fissure or an open fracture in the surface. This fissure is connected to a magma chamber below, either because of a magma plume in a hot spot or because of a subduction region. And the magma flow is then localized into a circular conduit or tube. So this conduit terminates at a vent or tube opening called a fumarole if it only emits gases. So a vent is where you get magma and gas, but a fumarole is if it's only ejecting kind of the vaporized gases that occur. Then you start to get successive eruptions that form a volcanic cone. So you start with a flat surface with just a little vent coming up. They start to build up, and as it erupts, it starts to build more and more material. So you start to get this kind of build up of an angle. And then at the top of the volcanic cone is a depression called a crater or caldera, depending on the size. So a crater is a depression that is less than a kilometer in diameter, and a caldera is greater than a kilometer in diameter. A caldera is usually produced by the collapse following a massive eruption, so something similar to Mount St. Helens. A crater is just kind of a depression because, as the lava erupts and cools, it cools around the actual opening, so you don't get that buildup in the center because that's where you've constantly got the eruption occurring and building up material outside it, and then, as it settles down, it settles, as the magmatic activity decreases, it settles back down in itself. And it's created this ring around. So that's why you have that depression within a volcano. So this is just showing how it's gone through many periods. Each color change is kind of a new volcanic event. This would be what we call the conduit from the magmatic chamber up to the volcano. Here's your crater at the top. You can also develop secondary vents along the edges of the volcano in areas of weak zones, and they get what are called parasitic cones. One well-known caldera is Crater Lake Caldera in Oregon. This formed from the eruption of Mount Mazama around 7,000 years ago, and this displaced the Klamath tribe of Native Americans. Wizard Island is actually this island located in the interior of the caldera, and it is a more recent volcano with a crater at its top. The surface elevation of this caldera is greater than 6,000 feet, and it is the 9th deepest lake in the world. And it is the 2nd deepest in North America. So this is just some imaging to show what the bottom of the lake within this caldera actually looks like. Okay, some of you may have heard the term supervolcanoes. These are a volcano that can eject 1,000 cubic kilometers of volcanic material, which, to give you kind of idea, this is 1,000 times greater than any recorded volcanic event in human history. We have never seen an event this large because these eruptions could cause regional to global extinction events. There are 7 active supervolcanoes on Earth. All are associated with caldera features. We have the Yellowstone caldera in Wyoming, the Long Valley caldera in California, and the Valles caldera in New Mexico. Those are the 3 that are located within the U.S. Additionally, we have the Lake Toba caldera in Indonesia, the Ara caldera in Japan, the Taupo caldera in New Zealand, and the Camp Flegrei caldera in Naples, Italy. Now, if you look at this, the Indonesian one is the largest caldera, the largest supervolcano on Earth. Yellowstone is a close second. Well, it's not close second; it's about half as big. But then, the Yellowstone one is the next closest by a significant margin. And I will post this video for you to watch. But essentially, Yellowstone supervolcano and Lake Toba, it's kind of a question of when they're going to erupt, not if, because they are still active. That's why we have hot springs. That's why we have geysers at Yellowstone. There is heat and magmatic activity below Yellowstone. And an eruption that large would throw up so much ash, so much debris into the atmosphere, and so much sulfur dioxide that it would actually physically obscure sunlight for a significant portion, if not all, of the U.S. It would decrease global temperatures because of the amount of sulfur dioxide and ash put into the atmosphere. which could cause a widespread, large-scale cooling period, not to mention all the actual pollutants of having these particles in the air. And supervolcanoes video, like I said, please make sure you take the time to watch these on your own. It's a really good way to get a visual for some of these concepts. Okay, next are shield volcanoes. These are produced by accumulation of basaltic flows. They are broad with a slightly domed texture, and they are most commonly formed over mantle hotspots in mid-ocean plate positions. Hawaii is the largest shield volcano on Earth. It is 9 kilometers tall with extremely low slope angles. There is actually a shield volcano located on Mars. It's the Olympus Mons. This is the largest known volcano in the entire solar system. It is over 14 miles tall. It is approximately the size of Arizona and originates over a presumed hotspot beneath the Martian crust. And like we talked about with plate tectonics, the lack of plate tectonics on Mars results in the extreme size of Olympus Mons. So because there's no method of transport over this hotspot, it just keeps building and accumulating in that one area. Next are cinder cones. These are symmetrical, steep-sided cone-shaped mounds of cinders and volcanic bombs. These are not solid rock. These are collections of loose material. They are basaltic in composition, and are typically the product of a single short-lived event. 90% of cinder cones form in less than a year. Therefore, they tend to be small, less than 1,000 feet in elevation. And if lava occurs, it comes to the surface near the end of a cone's life and extrudes from the base of the cone, not the summit. So if you look here, the lava would actually be coming out from the base underneath this cone. Next are composite volcanoes or stratovolcanoes, so this would be Mount St. Helens. These are large, tall, nearly symmetrical, cone-shaped, typically located in the Pacific Ocean and around the Mediterranean Sea. These are created by eruptions of silica-rich, viscous lava of andesitic composition that are too thick to travel far from their crater, which is what gives you those steep angles. You get alternating layers of erupted cinder, ash, and lava rock. Many have secondary vents and a long history of short, violent eruptions, punctuated by periods of dormancy. A very few continuously erupt, but a good example is the island of Stromboli in Italy. One of the most famous stratovolcanoes in history is actually Pompeii, and the eruption of Pompeii is what gave this type of formation its name. So these would be Plinian volcanic formations in lava, because the author Pliny the Elder is actually who wrote about the Pompeian eruption, which was a composite volcano. That's actually not going to be on a test, but there you go. Random piece of knowledge connecting this to ancient Latin and Roman history. So volcanic hazards. So the scope of the problem, what are the hazards, specifically to us? So there are about 70 volcanic eruptions per year on Earth. There is typically one large volume eruption per decade, which caused the most damage, and 500 million people live near active volcanoes. Over 25,000 people have been killed by volcanoes since 1980, and over 4 million affected by these same volcanoes. In the past 200 years, it is estimated that over 200,000 deaths have occurred from these eruptions, and the economic damage from volcanoes just since 1980 is estimated to be 2.8 billion. Some of the hazards are the pyroclastic flow. This is the downslope flow of hot gases mixed with ash and lava fragments. These are also known as noye ardentes, or a glowing avalanche. They can travel up to 60 miles an hour. The 1902 eruption of Mount Pelée in the Caribbean Sea was a very good example of a pyroclastic flow. The entire population was killed in a few minutes with just one single survivor. So this flow of this extremely hot gas and ash and lava moved downslope from the volcano so quickly that it wiped out an entire town. This is an image of a pyroclastic flow on Mount Pinatubo in the Philippines in 1991, which resulted in 350 deaths. So you can see how fast-moving and how massive these flows would be. So it's not just, you see kind of like a hill slope kind of coming down at you. It is this massive rolling cloud of debris. The second hazard is a lahar, or a volcanic mudflow. This is a mixture of volcanic debris and water. This moves downstream valleys and volcanic slopes with destructive results. Nevado del Ruiz eruption in 1985 in Colombia is a good example. It resulted in 25,000 deaths. So this is not that that hot kind of debris flow that we saw previously. This is basically a super saturated mix of volcanic debris, so the rock, the ash, the pyroclastic material that is mobilized essentially as a liquid. You can also get volcanic-related tsunamis or earthquakes associated with island or undersea volcanism. The volcanic ash and gases can also have impacts on aviation. Ingestion of these by plane engines can cause them to stall out, can cause crop failures because of layers of ash being deposited over these or completely burying crops and fields. Climate effects, it can actually have long-term weather pattern changes. So you can get short-term cooling, but it still has a much longer impact on the weather because of the gases erupted into the atmosphere and impacting the ozone. You have the weather effects, so the physical blocking of sunlight by the particles of ash, and the human and animal health effects, respiratory issues, mass extinctions related to megavolcano eruptions. Other landforms. There are other landforms besides just an actual volcano. You can get fissure eruptions and flood basalts, which create basalt plateaus. These are basaltic lavas that reach the surface through deep fissures in the earth. They may have enough volume to form regional basalt plateaus up to a mile thick. The Columbia River basalts and the Indian Deccan Plateau basalts are good examples of these. So the Columbian River basalts are from about 17 million years ago to about 5 million years ago through a series of north-northwest striking fissures. So when we talked about strike, that is the orientation. And it's a series of fissures kind of at that sort of angle. And the magma under them came from a mantle hotspot. And as North America has moved west, that hotspot is now below Yellowstone National Park. So it started up here, and it has migrated this direction. And these are, it's examples of these layered basalt flows from those fissure series. Other eruptions are the flood basalt eruptions of the Deccan traps, erupted over a period of 30,000 years. They are over 2,000 meters thick and cover 500,000 kilometers squared. And this activity actually caused a global temperature drop of approximately 2 degrees Celsius. The term trap is actually from the Dutch word for stairs and refers to the step-like landscape because of the deposition of the basalt. You can also get flood basalt eruptions, which are where billions of tons of carbon dioxide and sulfur are released into the atmosphere during eruptions. And both are very powerful greenhouse gases that contribute very rapidly to global warming. When it rains, the sulfur dioxide will come back down to Earth, dissolved in rainwater, so you get acid water, and this can actually kill vegetation on extremely large scales. If you destroy the vegetation in a region, the entire food chain becomes affected. And as the oceans are impacted by this acid rain, it can actually have effects on the marine life who cannot handle significant changes in the pH of their environment. So the way a flood basalt develops is you have a rising mantle plume near your oceanic lithosphere, and as your plate is moving, this plume rises up, and you get a partial melting, which create fissures, which start to give this series of flood basalt. And then eventually this basaltic region cools and solidifies, and as the plate moves, it moves away from that magmatic plume, and you start to get a volcanic trail falling behind your basaltic plateau. Other landforms are exposed pipes and necks. So pipes are the conduits that connect a magma chamber to the surface. We saw it in a previous slide. Necks are resistant vents left standing after erosion has removed the volcanic cone. So Shiprock in New Mexico and Deville's Tower in Wyoming are what's remaining from a historic volcano. So you have the volcano depositing material. Now this igneous material is more weather resistant than the volcanic cone around it because it is cooled and solidified essentially as kind of a single continuous unit, whereas the volcanic material around it are lava, but it's also mixed with surface material and your ash and your debris, so it's not as cohesive. So what happens then is that surrounding material weathers and erodes away. So you have your volcanic cone, your volcanic neck, your dike leading into the volcano here. All of that has weathered away, so we're left with just our neck and a bit of the remaining dike of the igneous material. Magma can also intrude into pre-existing rocks, and then erosion exposes these intrusive bodies known as plutons. We can get tabular intrusive bodies such as dikes. These are tabular-shaped intrusive igneous bodies that cut across layers of pre-existing rock. These dikes serve as conduit to move magma towards the surface. Okay, so here we're looking at a dike which offshoots from the magmatic neck through other units of rock. You can also get what are called sills. These are tabular-shaped intrusive igneous rock bodies that are nearly parallel to layers of pre-existing rock. Sills serve as underground layers in which magma accumulated. So here we get a sill because it is parallel to that boundary between the rock units, and here would be with the sill. This is showing a basaltic dike intrusion in the Grand Canyons where basaltic material magma has actually found a weak plane through this rock and filled that void. So which photo illustrates an intrusive dike and which illustrates an intrusive sill, and why? And I want you guys to think about this and try and do some research to answer that one on your own. There are also massive intrusive igneous bodies. The batholith is the largest. It must have a surface area of over 100 square kilometers to be considered a batholith. They tend to have granitic composition and take millions of years to emplace. The Sierra Nevada mountains in California and the Black Hills of South Dakota are examples of exposed batholiths. Stock are intrusive bodies with areas of less than 100 square kilometers, so that's the only defining difference between a batholith and stock. And a laccolith is an igneous intrusion that tends to lift and dome the sedimentary rocks below or above it. So here's an example of a batholith. So you see the size here is tens of kilometers wide. A stock, which could be an offshoot of a batholith, is just a few kilometers wide. And then a laccolith, which actually intrudes into a unit, but instead of continuing to push through the rock, it actually forces it up in an upward warping. Here's an example of a laccolith in Montana, and then the Yosemite batholith in California. And here's another video just showing intrusive plutonic features, kind of an artist rendition. So that is the end of the slideshow for igneous and volcanic activity. Like I said, I'll post all the video links for you on the class site. Your discussion